Hey y'all, this is JD Cook here from IndexCoop. So we ran this OurNetwork Learn session a couple days ago, but our recording got there were some issues with the recording. So I'm actually re-recording this lecture, just hitting the slides, the main things we covered. This recording will likely be a little shorter because we won't have live questions, etc. But want to make sure we get this content out in a digestible way. So again, I'm JD. I lead analytics at the Index Co-op, the analytics working group. I've been contributing to the co-op since November of last year, so about a year now, and have been doing it full time. Got hired by the Dow full time in April, I believe, or started full time, went full time. The hiring came a little bit later, like early summer, but yeah, we have a great analytics team at the Index Co-op, and really happy to be a part of OurNetwork Learn, both as a lecturer and mentor, but also Index Co-op is one of the sponsors. So we're excited about sponsoring this group of students, learning about Web3 and crypto data and analytics. So today we're gonna do a little bit of smart contract event review. We're gonna focus on some SQL skills with joins and unions. And have some exercises to work through as well. All right, so smart contract events review. We're gonna actually just jump right into this query that I have already made. So this is gonna focus on a smart contract that's core to the Index Co-op. The Index Co-op is built on set protocol infrastructure. I'm gonna open this contract. This contract is the basic issuance module. The basic issuance module, this is where any simple index products, so we're talking from the Index Co-op's perspective, DPI, MVI, BED, and data are our 4 index products we've launched. We also have E2XFly and BTC2XFly, but those are leverage products and they have a different issuance contract. But the basic issuance module, this is where index products are issued and redeemed. And what I mean by that is, what we see is set token issued event here. DPI, let's use DPI as an example. It's a token that gives you price exposure to an underlying set of tokens. So I can't remember the exact count in the moment, 15 something tokens in DPI. And the way DPI is created is those underlying tokens in the right token amounts according to their weights have to be sent to the contract, and essentially you're exchanging those underlying tokens for one DPI, and then there's secondary liquidity, so you can trade that DPI. But one token of DPI is really a claim on these underlying assets, and therefore one DPI gets price exposure to the combination to these assets. As a whole, and that's what an index product does. It gives you exposure to a wider sector, only having to hold one asset. So this contract holds those events and the functions that allow you to mint or redeem DPI using the underlying assets. So we have this set token issued events. I believe this event, we can search here in the contract code, is under the mint and burn. So minting will be, you're minting new DPI and it's getting issued. If you're burning it, it's getting redeemed. So here we have the issue function. So we have the set token being issued, the quantity being issued, and who it's being issued to. And we can see at the end of this function, we're emitting this event where the set token, the issuer, who it's being sent to, put contract, and the quantity being issued. So we know from previous lectures, right? These event logs are stored on the chain. We look at these events. We have we have our function signature here in topic 0. We're going to have 3 indexed topics: the set token, the issuer address, and the to address. And then we have these 2 other fields stored in the data. We have a hook contract address and the amount. And so Dune's doing the work so we don't have to. So they're decoding these logs and putting them into nice, pretty tables for us. So this contract's already been decoded on Dune. So we have a set protocol v2 basic issuance module, set token issued event. So this query right here, where set token is equal to this address, this is the MVI address, the metaverse index. So this query is going to pull all events where a set token is issued and their quantities. So what we can do with these specific events is we can do a really quick and dirty unit supply for MVI, where we take the sum of all units from the event issued. We're going to union that on the negative sum of all units. So that would be the sum redeemed. And we can just take the sum of those 2 things. We can run that. We get 187,202 units. Let's do a quick check on CoinGecko, see how close we are. We have 187,897, so about 700 units off, which not sure if that's on their end or if certain events haven't been decoded yet, but we're really close on unit supply, just triggering those events. So tale of 2 queries here. Sorry for the jumping around right there. I wanted to highlight kind of the importance of events. So events, this is how we track data on the blockchain, and they're really modular in the sense that you're tracking specific things that happen at a specific point in time. And it's really through the combining of these events that you start to tell stories about users, or in our case, a lot of time users on the blockchain. So I'm going to open these 2 queries. This first one is a simple query to get the number of current addresses holding DPI. And it's just using the event transfer abstraction on Dune. And it's saying, hey, anytime index is transferred out of a wallet, subtract that amount. Anytime it's transferred into a wallet, add that amount. And let's just aggregate those and find the count of distinct addresses that have greater than 0 total amount at this time. And that's pretty simple, right? 33 lines, and we have, a rough count of 15.8 thousand, or 15,000. Yeah, 15.8 thousand. So now I'm going to jump over to this other DPI address exposure query. The reality is just looking at the addresses that hold DPI is not an accurate foundation for the IndexCoop's perspective of address exposure. Because this is a product that we hope drives value to users and can also be used in many different ways, we actually have to track their exposure through many particular avenues or events. In the lecture we talked about what those could be. Those look like liquidity pools. As a holder of DPI, you could supply liquidity on Uniswap v2 or v3. There's money markets, there's Aave, Fuse pool. These are all opportunities to use DPI, but you won't necessarily have DPI in your wallet. However, you still have exposure to it. You still have the claim on the DPI. You can pull it out of a money market. You can pull it out of a liquidity pool. So our address exposure queries are much more complex, where we're traversing through events on Uniswap v2, on SushiSwap. Right here, we're going to be going through events on Uniswap v3. to pull liquidity from there. We'll go through, and we're constantly updating this, right? Like as DPI gets added to new money markets, etc., we're updating this so that we can have an accurate representation of who has exposure. In this case, we're doing just a simple unique address exposure over time. It's 900 lines, and we end up with just this chart that kind of shows us over time, at any point in time, how many addresses have exposure to DPI. But this is also a foundation for us knowing how much address exposure each address has, which we use in other queries. We just want to highlight how events, come together. They're modular. We have to look at events from lots of different contracts. We have to put them together, evaluate them together to tell the proper story or about our users. So again, this is a part we'll skip through. No live questions on this recording. We had a few in the original lecture. So because we're pulling data often from many events that are happening in many different protocols, different abstractions, we have to be able to combine this data well, and that's where we're going to get into some SQL skills here on joins and unions. Joins allow us to combine data from multiple tables against a common keys. So columns that are the same in two different tables, we can find and join rows that have observations in both tables, in one table but not the other, and so on. So there's a few different kind of joins. I think this picture is a good representation. If you have two tables, there's lots of different ways you can potentially combine data between the two, or exclude data depending on what your goal is. So we're going to go through, we have this query here. We're going to go through some quick examples. And the goal really here is to just provide you with some initial examples that help you illustrate in your mind like how a join's working, what data it might include or not include. So we'll probably run through these pretty quickly, yeah, hopefully it'll be helpful, and obviously this query is available to fork and play around with at any time. So I created these two, copied actually from the Postgres tutorial, some of the examples there just for simplicity, and also so that if people want to review that documentation, they have the examples already built out for them. Two baskets of fruit. We have basket A that has an apple, an orange, a banana, and a cucumber, and basket B that has an orange, apple, watermelon, and pear. So let's do this inner join first. An inner join returns rows that are both in the left and the right table. So that's this topmost, the top diagram here, Venn diagram. So we're looking for the intersection of the two tables. So if we select everything from A and B interjoined on fruit A equals fruit B, got something commented out down here. All right. Then we get, so they're joining again on the key is fruit A equals fruit B. So we know that there's an apple in both baskets and an orange in both baskets. They have different IDs, 1 and 2 and 2 and 1, but we know that there's both an apple and an orange in both. Okay, a left join. So when we talk about a left join, think about left being, you have your two tables. It's the first one you bring up in the query. That's your left one. The second one's your right one. So we're going to left join from basket A. So basket A becomes our first table or our left table. And then we're going to left join basket B onto it. And a left join returns all the rows in the left table as well as corresponding rows in the right table. Oh, I gotta not highlight that. Okay, so here we go. We got all the rows in the left table, and then where fruit A equals fruit B, we're also returning those rows, that data from the right table. So left join. I would say left joins might be the most common join because you're typically starting from some data set and trying to add data onto that to complement whatever data you already have. Okay, so left outer join. So a left outer join is going to be on the left side of this, the left side, the second diagram down. It's all the data on the left table that is not in the right table. So we should expect this. If we look at this original left join, this query should return all the data that's in the left table that is not in the right table. So it should return banana and cucumber. And we do that by saying, hey, let's do a normal left join, but where B is null. So here we have where B is null. Doing that. Not normal. All right. And there we have it, banana and cucumber. So right joins are the same. I gotta figure that out. Sorry for hypnotizing y'all. Right joins are exactly the same. It's just saying your first table is different, right? So again, if we are selecting from basket A and joining basket B, the right join will just say start with basket B, then go to basket A. So it just switches the tables that start as the reference point. So a right join will turn all rows in the right table as well as corresponding rows in the left table. So it's similar, but now we have all the fruit from basket B, and we're returning the apple and orange as well from basket A. And the right outer join, it's going to be the same. We're going to now return all the fruit in basket B that is not in basket A. And that's going to be the watermelon and the pear. Okay, so a full join, it's essentially going to return everything. It's going to return a set that contains all rows from both left and right tables, with the matching rows if they're available. So let's run this. So here we say essentially all rows or all data from both tables is represented, and they're matched where applicable with the apple and the orange. And then a full outer join. Run this. This is going to say all. So this is going to essentially exclude the intersection. So if there's a fruit in both baskets, it's not going to include it. So it's returning rows from both tables that do not have corresponding rows in the other table. So the fruit that are unique to basket A and the fruit that are unique to basket B. Full outer join. Again, I should probably be referencing this more. A full outer join is this bottom right most diagram where the intersection is not included. All right, so we got two more. These are a little bit different. Cross joins. We're going to start with a cross join. So cross joins are actually pretty nifty and pretty helpful. So a cross join, what it does is it's going to produce a Cartesian product of the rows in two tables. And to illustrate this, I've created a simple table that's called dates that it has all the days in October. And then I have a simple table of numbers that's numbers 1 through 10. So if I select dates, it'll just be dates. This is just going to be dates. Oh, forgot my from. So here's all our dates in October. And then numbers. This is going to be all our numbers 1 through 10. So then if I do this cross join, again, it's going to produce a Cartesian product. So every combination of the two. Let's run this and look at it. It'll illustrate it. So now we have every date, and every date is represented with every single number. So 1 through 10 for every single date. Cross joins have been helpful. Like one example is you are trying to produce something over a specific date range. You can generate a series of that date range and then join, cross join. So like say you're trying to do address exposure over the month of October. You can generate all dates in October, cross join the addresses, all unique addresses in October. You get an address by date for all of October, and then you can join whatever other columns like exposure to a product onto that, and you can create like a running sum throughout a range of dates. All right, the last one is a self-join, and self-joins they use regular joins. So they use regular left joins, right joins, etc. It just refers to when you join a table onto itself. So we have this employees table. Let's look at it really quick. So here we have these employees. They have an employee ID and they have a manager ID. And self-joins are particularly helpful when your data is hierarchical. So in this case, we have a manager ID that references back to the employee ID number. So for employee ID 2, Ava Christensen, her manager is employee number 1, who we refer back to employee ID number 1, and that's Wendy Hayes. So if we wanted to say, hey, I want the name of every employee and then the name of their manager, we can just do that by just using this table itself, using a self join. So we're going to get the first name and concatenated with the last name of every employee, and then that's from employees E. Then we're going to interjoin the same table, give it the alias M on employee ID equals manager ID. And so this self join allows us to see every employee, their name, and their manager's name right off the bat. Okay, so those are the common joins. Again, this query is available if it's helpful to just run through them, look at the data, try to figure out in your mind how it's combining or excluding data. That's the main goal. We're going to hit an exercise in a minute that allows us to work with joins a little bit more. All right, so similarly, unions aren't generally as performant as joins, but good to know about them and can be useful in situations. There's 3 main unions we're going to focus on, which is call them union, intersection, and except. In some SQL languages, SQL formats, it's called minus. But let's jump into the student query again. Same thing. This is available for anybody to fork and play around with. Our data here is films. So we have top rated films and most popular films. So let's look at these really quick. Make sure nothing else is. So if we're looking at all the top rated films, we have Shawshank Redemption, Godfather, 12 Angry Men and their years. And then if we look at the most popular films, we have American Pickle, Godfather, and Greyhound and their years. So the thing with unions that you have to remember is you're not like joining columns by a specific key. You are more combining rows that have the same columns. So in order to do a union, you essentially have the same columns in two tables, and then you're trying to combine them according to some criteria. So again, you notice in both most popular films and top rated films, we have two columns, title and year. They're the same. So a union, like the keyword union, the goal, what the union does is it's going to combine, so let's do this, select all from top rated films, union, select all from most popular films. So it's gonna combine the two sets together and exclude any duplicates. So it's gonna say, hey, what are all the films that are represented in either of these two? Just unioning them. If you do a union all, so if you were to include the all keyword right here after the union, it will actually include any duplicates. So you notice that Godfather was represented twice. It's in both data sets. A union all can keep that duplicate. A union will not. A union only gets distinct or unique rows that are from both data sets. All right, an intersection is the next one. It's pretty self-explanatory. It's going to get rows that are available in both data sets. So the row has to be in both data sets to make it in an intersection. You're finding like I said, pretty self-explanatory. You're finding the intersection of the two data sets. The only one that's in both is the Godfather. All right, except returns, okay, except is going to return all the rows that are in the first table and are not in the second table. So let's run this except. Select all from top rated films, except select all from most popular films. So it's saying, hey, get all the top rated films that are not also most popular. We can do the opposite. We can get all the popular films that are not top rated. So these are ones, maybe got gypped on their ratings. They're very popular, but didn't get a top rating. The ones that we did first, these top rated, these are the ones that were rated high, but maybe got a little more credit than they deserved. Not as popular. So those are the main three unions wanted to focus on: union, intercept, and accept. So that was, again, much simpler than joins, but use this query if you ever want to play around with those, and again, illustrate in your mind how these unions are working. All right, so now we have two exercises. This is a part that will probably go a lot faster just because we're not going to be doing it live. The first one is create a price feed. This will involve a couple things. We wanted to introduce the prices table, the prices.usd table in Dune, as well as work on our joins. So let's see, I might have updated this. So take this away. Forgot to update this after actually doing the lecture. So this exercise, create a price feed. Want to introduce you to prices.usd table. So this is an abstraction built in Dune that tracks by the minute the price of given assets. So if I run this selection here, this is going to select all from prices.usd where contract address equals the DPI contract address. And let this run for a second. I think it'd take too long. Maybe I was wrong. This exercise is going to be what we would do. Oh, there it is. We have by minute the price of DPI. It's going to have the symbol, the contract address, and the decimals in DPI. But there's often times where where prices.usd does not have an asset included yet. So there's not just a price table for you to use in Dune. And so you have to build custom price feeds using events on the blockchain. And we can do that. So we can do that using the DEX pools that are on the DPI that have DPI. So this event right here, pool created event on Uniswap v3. This address, because I know this pool, I interact with this pool. I'm selecting the event where the DPI ETH Uniswap v3 pool was created. Right, and we can see the DPI token here. We can see the wrapped ETH token address here. The fee, it's a 0.03% fee, etc. The pool address. Okay, so I'm giving in this exercise the base, the starting point, which is the swap events. So we don't have a DPI to USD price. But we do, based on the swap events, have a DPI to ETH price. Because every time a swap happens, that's essentially stating the current price in ETH terms for DPI. So what this is simply doing is saying, hey, look at all the swap events in Uniswap v3, where for this pool, we're going to aggregate to the hour and get the average DPI price in ETH terms, just by saying, hey, what was the amount of ETH over the amount of DPI. So let's look at this really quick. All right, so we had some weird stuff, which often happens when pools are initiated right off the bat, but right when the pool was initiated on May 7th, it was 1 DPI was worth 0.161 ETH, right? So we do know that ETH is in the prices.usd table. So the whole point of this exercise is, can we take this swap price base and create a price feed that gets us by hour the DPI price in US dollars. So if you're working on this, fork this query. And what you can just do, because we're doing a recording, we did this kind of live at the time, but just pause this recording here, take as much time as you want to try to work this out and build this price feed, again, to get the DPI price in US dollar terms. So pause the video here, go work on it, but I'm going to keep going. I'm just going to put in the solution here so we can run through it. All right. Adding in one simple solution. You can do this probably a few ways, but just work it out really quickly. Again, we have in prices USD, this is the same ETH contract address, that wrapped ETH contract address that we found in the pool created event. So we know this is the asset that's on the DPI is trading against in the pool. So we can just take prices USD, where we're looking at this asset, again, aggregate at the hour level and get the average price. So this will give us a result. Let's run it really quick of, this actually might take a minute. Probably should have. We'll see how fast it runs, but this will give us a result of an hourly price for wrapped ETH. Now, there you go. This price actually goes way back because Ethers existed for a long time. Now we can use a join. So we know in the DPI swaps table, we have the hour and the swap price from DPI to ETH. And now in this other ETH USD CTE, we have an hour and the USD price of ETH. So we can select the hour and the swap price from our original swap CTE. And then we can left join. So we have that table, and then we're going to left join on the hour. So we're going to bring in data from the ETH USD table. On the hour, we're going to bring in the ETH price in USD. So we're going to multiply that price. So we gave that second table the alias B, the first one the alias A. We're going to multiply that price by the swap price, and that will give us a USD price. And then we know the pool only existed from May 7th on, so I just included this date filter just to speed things up. Let this run for a second, but this essentially, using prices.usd and a left join with the swaps feed, we can now get a price feed by the hour for DPI. There you go. There's actually a solution to this. I think it'll probably be updated in this now, but I'll take this away so that if you fork this from now on, don't just have the solution sitting there. I have another query that's named the same thing but solution in my Dune account, so if you need to reference that. All right, that's the first exercise. Let's do the second one really quick. So this one is we're gonna run through this one really quickly. Only have a few more minutes left, but this one is based on one of the IndexCoop sponsored questions for the OurNetwork Learn program, and that is, we want to analyze our DPI Uniswap v2 to Uniswap v3 migration. In early August, we incentivized migration via the v3 staking contract into the v3 pool because we're trying to take advantage of the concentrated liquidity there. So this exercise is intended to help us get some, oh gosh. Why is this not working? Let me go here. This link's not working. Okay, sorry about that. This exercise is going to just help us look at some events around those pools and practice some quick unions. Let's see here. So really quickly, again, because I'm low on time here, the prompt is here. So I already said we incentivized this migration. We have the links to the analytics pools. So this is like the Uniswap analytics pages. So you can see, you actually can look at the beginning of August in both pools, and you can see V2 drop pretty dramatically and V3 rise pretty dramatically. These are the actual pool addresses here. So the events it's going to use is this pair event mint and pair event burn. This is for both Uniswap v3 and v2. This is the event when liquidity is either added in the case of minting or taken away in the case of burning. We're left joining Ethereum transactions to actually get the from address. So this is the address of the liquidity provider. So I've provided these v3 minting and burning events, as well as v2 minting and burning events, CTEs. So those are the foundation. And the idea is there's a list of questions here, prompts that we can use to practice with some simple unions: union, intersect, and accept. So let's, I'm actually going to go to really quick my solutions so I can put it in. Again, this would be where you'd want to pause the recording if you just want to work on these and work on them for as long as you want. But I'm going to continue so that we can wrap this up. Again, I have a solution one already built. I'm just going to grab those. Actually, I'll just work from here. So list the LP addresses again. So we have the V2 and V3 mint and burn events. List the LP addresses that have minted liquidity in V2 or V3. So we just want unique addresses that have been in both. That is achieved simply by doing a simple union. We union V2 minting and V3 minting, and we get we answer that question. The LP addresses that have minted liquidity in both V2 and V3, this is an intersection. An AND signals an intersection. They have to appear, the LP address has to appear in both V2 mint and V2 burn, not or. So we're finding the intersection. We'll use the intersect keyword to answer that question. list the LP addresses that are minted on V3 and not on V2. So we want to find any addresses that have only been on V3, that only got into providing liquidity once V3 was launched. So that will be an accept. We're pulling all the addresses from V3 and then excluding the ones in V3 that are also in V2. That's what an accept is doing. All right, so this one's just adding in some dates because August was the specific time when the migration happened, in the middle of August. List the LP addresses that burned V2 liquidity in August 2021 and minted V3 liquidity in August 2021. So this is essentially who stopped providing liquidity in August on V2 and then went to V3. And that's, this is a very foundational way to start answering who actually migrated. So we're going to look at who minted in August in V3 intersected with who burned in August on V2. The LP addresses that are in both of those scenarios are potentially the ones that migrated directly. All right, and the last one, the LP addresses that have minted both V2 and V3 liquidity, but have not burned V2 liquidity. So this is somebody that maybe has liquidity in both places, but they still have liquidity in V2. So we're going to take the V2 mint. We're going to say, hey, we want all those that have minted on V2 and V3. That's the intersection of those two. And then once we have that intersection, we're going to say, hey, we want all those that are there except ones that have burned on V2. So they've never actually burned any liquidity so they've never actually burned liquidity on V2, but they have added liquidity to both V2 and V3. So that can be done with an intersection to find those that have minted on both, then an accept to take out ones that have burned on V2. That's the answer there. All right, that's gonna wrap it up. Again, you can work on those exercises on your own. Everything on the slides is linked, so you can make sure this link's working, but everything on the slides is linked, so you can work at your own pace. And yeah, again, happy to be a part of the OurNetwork Learn and have IndexCoop sponsoring. Appreciate y'all. We'll catch you later.